All right, by request 10.4, number 35, find the area inside the larger loop and outside the smaller loop of the following polar function. R of theta is equal to 1/2 plus cosine of theta. Drawing this, I'm just going to quickly put something together here. We have this coordinate system. It's technically only needing the right horizontal axis to be actually a polar axis, but not a big deal. Anyhow, when theta is 0, so we're facing that way, we can see the cosine of theta will be 1 plus 1/2, or so we get out all the way out here to 3/2. So 3/2 is what the radius is when the angle is 0. It'll start carving out in the counterclockwise direction. When you're at theta equals pi over 2, cosine of pi over 2 is 0, so we're only out at a distance of 1/2. It actually kind of looks like this when it curves out. Bows like this. Maybe not as terrible as that, but close enough. At theta equals pi, cosine of pi is a -1. And so 1/2 minus 1 is going to be a -1/2. So it'll be back here. So remember, we're facing an angle of pi, and the radius is going to be a -1/2. So that just means that the loop has done this. Okay. And if you need to review graphing polars, you could watch the videos that I have online about that. And the rest of it's very symmetric to this, so it's going to look sort of like, if I draw it well enough, like that. Okay, and it keeps following this path. Okay. Anyhow, we want to know the area inside the larger loop, so inside this larger loop, but outside of that inner loop. So basically, we want to know what the area is of this shaded region. So it's important for us to find out, when do we complete this larger loop? When do we go all the way through here, all the way to this moment right there? That's what I want to know. So that's going to be important, right? But not only that, we're going to have to, if you did that, this is kind of a tricky problem, because when you do this problem, this inner loop here, and let me go ahead, maybe I could do a back on this. I'll try to do this properly. When you use a different highlighter. When you find the area from, let's say, angle 0 all the way to whatever angle it is that you end up back at the pole there, you're going to end up getting all of this area. Now, if you look at that entire area, you've actually shaded over that loop. So we need to remove that loop. Now, there's something kind of dangerous about this problem in that, let's say, well, we do know that we start that first, I'm only looking at the upper half here, we start that at an angle of theta. And we add up all that area, and remember, all that area is adding up all the way, and it's actually shading in this stuff as we do that. It's shading that in. We want to remove that, right? So we want to find out first, when does the radius become 0? So that's actually my first question. When is the radius equal to 0? Right? Because I want to know, when do I get back to that pole? So that just means that we solve 1/2 plus cosine of theta is equal to 0. And of course, that means that cosine of theta is -1/2. And we know that that the cosine is negative in quadrants 1 and 3. So, and its reference angle for that to get an output of positive 1/2 would be a pi over 3. So, but we are in quadrants 2 or 3 because cosine is negative. And you can see that it will actually be, we're facing some angle this way in quadrant 2, and it's drawing back to our feet there. So I'm going to use the quadrant 2 angle. So that will imply that theta here is 2 pi over 3. That's a quadrant 2 angle with the reference angle of pi over 3. So here's the deal. I get all of this stuff, including that inner loop, shaded from angle 0 to angle 2 pi over 3. So let's go ahead and at least start with that. So the area of the first region is going to be, remember, it is the integral from theta equals wherever we start, which is 0, to theta equals wherever we're ending, which is 2 pi over 3, right? And it's 1/2 r squared d theta. That's the formula. And I'll actually leave it like that for now because I'm just I just want to kind of move forward in the problem. The next thing we need to lose is all of this inner loop right there, that top inner loop. And that top inner loop, let me go ahead and remove that, starts when I'm facing an angle of pi. When we're facing an angle of pi, cosine of pi is -1, so 1/2 minus 1 is -1/2, so we're right here. So remember, following my direction following my direction arrows. By the time I'm facing an angle of pi, this is -1/2, comma pi. I am then going to subtract off area 2 from this integral, and area 2 is going to be the integral starting from an angle of pi and going all the way to an angle of whenever we get back to the pole. So here we were facing an angle of pi. Let me draw it in a different color. We're facing an angle of pi in this direction, and that starts us back at that -1/2. And as we turn, once we're facing this direction, we'll finally have carved out this upper loop, and we can erase that area. And we already know when we're going to be back at this origin because we have actually solved it right here. That we are back at that origin at a reference angle of pi over 3 when we're facing into quadrant 3. So that is 4 pi over 3. So this will be to 4 pi over 3. And again, 1/2 r squared d theta. Now that is the area. So essentially what we've done is we have found all of this region, all of that stuff right there. That was from 0 to, was it 2 pi over 3? And then what we did is we took out this area, which was the region from pi to 4 pi over 3. And of course, that will only give us that green area there. And we need to double that up because they want us to find the total area. So I'm going to double that up. So total area is twice the difference between area 1 and area 2. That's twice times. They both have a 1/2. Integral from 0 to 2 pi over 3. R squared d theta. Minus 1/2 integral from pi to 4 pi over 3. R squared d theta. And obviously, you can distribute that 2 in. This will be the integral, 0 to 2 pi over 3. R in this case is 1/2 plus cosine of theta, so I'll just square that. When you square that, you get 1/4 plus cosine of theta plus cosine squared of theta d theta. And you're losing the integral from pi to 4 pi over 3 of the same, right? 1/4 plus cosine of theta plus cosine squared theta d theta. There, by the way, if you're looking at this and you're thinking you did a different way, there are several ways to do this actually. All right, so antiderivatives. So the antiderivative of 1/4 is 1/4 theta. The antiderivative of the cosine is the sine. And we have that cosine squared. That's 1/2 1 plus cosine of 2 theta. It's the half angle identity. And we're going to lose, oh, by the way, these two pieces right here are from 0 to 2 pi over 3. Should have written that in there. Sorry about that. And we're going to lose 1/4 theta plus sine of theta. That is going to be evaluated from pi to 4 pi over 3. And we're also going to lose 1/2 from pi to 4 pi over 3 of 1 plus the cosine of the double angle. A little bit of work in there, right? Not too bad though. All right, finishing this out, let's see, plugging in 2 pi over 3, we will get pi over 6 plus root 3 over 2. And then if you plug in zeros there, they disappear. So plus 1/2 theta, let's see, plus 1/2 sine of theta, sine of 2 theta, sorry, from 0 to 2 pi over 3. And let's see what else we're doing. We're losing from that, minus. This will be pi over 3. I'll distribute the negative, pi over 3. And then sine of 4 pi over 3 is, oof, maybe I shouldn't distribute that negative just because it makes it a little bit more confusing for me, minus root 3 over 2. Let me double check my math there. I think that's right. That's right. That's right. Oh, and also we'll lose pi over 4 from this, right? Because you're evaluating the top. And so you have 4 pi over 3 times 1/4, which is pi over 3, and sine of 4 pi over 3, which is negative root 3 over 2. And when you plug in pi, you get minus pi over 4, and then sine of pi is 0. And then minus 1/2 times theta plus 1/2 sine of 2 theta, evaluated from pi to 4 pi over 3. So a little bit of simplification here. When I say a little bit, it seems like a lot, doesn't it? Let's see what I can do here kind of quickly. Actually, I probably shouldn't. Let's see, pi over 6 plus root 3 over 2 plus 1/2 times 2 pi over 3. Most of this is going to be arithmetic. Maybe I should fast forward through this. Okay, after simplification, well, sort of simplification, evaluation. We're at this point. I'm going to pause it again and finish this out. And we get to this. It was a little bit of work in the background to do that, but it does simplify nicely, and that is the correct answer. A couple things I want to mention here when you're doing this problem. One, we could have done this going from 0, angle 0 right here, all the way increasing, all the way to here, which is angle 2 pi over 3, right? And then subtracted off technically this region because that region is the same area. So you could technically say, well, I'm going to lose the region from 2 pi over 3 to pi. You could totally do that. I just personally like to use the actual region in question, so I just chose to use this region right here, which starts at pi and ends at 4 pi over 3. I guess there wasn't a couple things. It was just that I wanted to mention. All right, this is done.